So first, I want to thank the reorganizers for the invitation. And also, I want to thank Misha for the introduction to toric code. So the topological phases. So that's basically what we'll talk about in a totally opposite abstract way. So this talk is all about speculation. So not much I can prove. So what I'm going to talk about is already Misha mentioned the word topological order. So it's a new kind of topological phase of matter. And I want to take a point of view about the modularized space of all the Hamiltonians can realize this topological order. In particular, the toric code, which already we know exists in nature, but his Hamiltonian will be different from mine. And as a topologist, I want to ask, what's the topology of this space? And I will speculate. And this came from something completely unexpected, actually. We are talking about a new kind of error correction code. That's actually led us to this discussion. So to start with, I want to say, I don't have a definition of what is the space of Hamiltonians which realize a topological order. If you not have heard of topological order, it doesn't matter, just think about toric code. That's the only one we'll talk about. So I will also focus on two spatial dimensions, which are anyon models. So suppose you give me an anyon model, in particularly the toric code, which I already realized in this lab, different Hamiltonian. And I will ask the question, suppose I consider all the Hamiltonians which realize this topological order. And I will only think about spin system, no fermion. I will think about only a fixed finite dimensional Hilbert space. And I want to make the Hamiltonian local, which I call physical. And there's no easy definition mathematically what it is, this space. And there are lots of subtleties, but I will behave as a physicist, just say, oh, we know it. And I can just mention a few subtleties. First, there's microscopic, which is always a problem for convergence of Hamiltonians. Second, there's an issue about topological order. And the third, the word realize a topological order already needs definition. So there are lots of subtleties, but I won't talk about it. But now, also I want to mention, I will consider gap Hamiltonian not necessarily local commuting projector. So it's a slightly bigger space. And then basically I want to ask you the question, what is the topology of this space? Or where the topology come from? How to categorize it? And in particular, I want to talk about homotopy type. What is the homotopy groups? And I will make a conjecture on this. To convince you there are topologies, let me talk about the toric code, which Misha realized in the lab. So I won't really define it. So I assume we all know it and we know it exists in Rydberg atom. So I want to give you a non-trivial loop inside the space of Hamiltonians, which realize the toric code. So you take the lattice, which is the triangular lattice, and you pick all the triangles which sit you the way you want, which is like this, the base at the bottom. And you color them by 0, 1, 2. You forget the other opposite triangles. And you color them by 0, 1, 2 so that for each of the big hexagon, they have always 0, 1, 2 at each vertex. And then you write down only three Hamiltonians, h to the r, which is h 0, 1, 2. And let me just do 0, and then we'll know the other two. So if you take 0, and what you do is you pick the 0 plaquette, a plaquette which colored by 0, and then you write down poly z on this 6 qubit. So I have a lattice model, and there's a qubit on each vertex. And for each of these 0 plaquette, I will have poly z on this neighborhood opposite triangle. And on the type wall 2 triangle, I have a 3 poly matrix X. And I will do 0, 1, 2. So there are 3 of them. Now I have 3 Hamiltonian, which is the vertex of a triangle. I want to make a loop, so that means I need to continue from one to the other. And that's this small quantum circuit give you. And I won't really give you the quantum circuit, I just tell you what they are because completely written down in the paper which I mentioned. So this circuit actually have a deep physical origin. So this is the famous Cranian-Warner duality. So what you do is take a triangle. You imagine, for those who speak the language of anyon, you have 3 sigma anyon on the edge, and then 2 sigma can fuse to wall side, and you have a Hilbert space here. And then you put a sigma loop inside and fuse to the boundary. And I claim that's a version of Krenner-Warner duality in this context. And that's basically the unitary you want. And then you can write down a split formula to conjugate from one vertex to another, which are the 3 Hamiltonian I define. And I claim that's a loop. And the question is, how do you know that's non-trivial? And I will show you that's actually realized a non-trivial symmetry of the toric code, which is the famous EM symmetry. So that's how I know it's non-trivial. And that's actually, I just want to show you that a really topology in the space of Hamiltonian, which realize a fixed topological order. So now let me first give you a fibration, which what I want to do is Alexei Kitaev has been working on a similar problem for so-called invertible one for the last decade on and off. And that's a problem too hard for me, so I want to module that problem. So the way I do it is that inside the space of Hamiltonian, which realize a topological order, there's a subset which realize so-called locally definable topological order. Nowadays called invertible. And I want to module them out. And you can take any topological order, stack on a so-called invertible one, and that's an action. You can just take the quotient space. And that's what I call the intrinsic part. And I claim there should be a fibration like this. Actually, I cannot even decide if it's a product or not. I think the homotopy group seems like a product. So for now, I will just work on this guy, which I call the intrinsic part, which is modulo all the invertible ones. So now my question is, what is the nature of this space? What's the topology? And I want to claim this is more or less a classifying space of the topological order. Okay, so that's what I want to convince you. So this is basically behave as a classifying space. In order to do that, I'll have to talk a little bit of symmetry. And actually, I'm glad to see Pavel's here. Victor's also here. I forgot to put down the name, the word yin o. So there's a beautiful, beautiful, incredible theorem which says in the context anyon models, symmetry and the defect are the same thing. Okay. So what it means is the following. So suppose you give me an anyon model as what Misha showed you. It's a 2D piece of material. And you can imagine the possibility, I think Misha can do it. You can introduce domain wall inside the system, okay? And what I want this domain wall to be acted as a property called invertible. It means that if you take one domain wall, another domain wall, you can put them together and just annihilate them. So I claim this kind of invertible domain wall by a mathematical theorem of yin o, that's exactly as the symmetry group of an anyon model. And it's just this cartoon picture. It's very, very easy to see why there's a map. So suppose you have a topological physical method. The only one I will talk about is toric code, and you have a domain wall. And you have anyon on the left. And you can just push the anyon across the domain wall into this configuration. Just go through the domain wall and drag with it. And then the domain wall is invertible. So that means these two, one go this direction, the other go the opposite direction, they cancel each other. So therefore, you're left with this picture. So on the right, you have an anyon wrapped inside an invertible domain wall. And that's your tensor function. And that's your symmetry. Okay? So that's the map from the invertible domain wall to tensor autoequivalent. We have two experts here for you to show this map is invertible. And that gives you the identification of the invertible domain wall with a tensor autoequivalence. So now I will talk about symmetry as invertible domain wall by this theorem. And to study domain wall, that's really started by the oracle Kitaev on this subject. So he studied gapped boundaries. And domain wall can be turned into a special case of gapped boundary. You just take this piece and you fold it. It's just a gapped boundary from two pieces. Actually, it's the anyon model dual to vacuum. So the same thing as study spatial gap boundaries. And this is the famous paper we started, tells you there are two different boundaries for toric code, which again, which I can realize in the lab to realize the topological qubit. So now I want to make basically the main topic of what I want to say in this talk, which is I claim the Hamiltonian modulo the locally definable ones is the categorical classifying space of the categorical symmetry group of anyon model. So let me explain for those who don't speak this higher categorical language. So the anyon model mathematically is a modular tensor category. And the word category just means that you, instead of have, set theory, and you have a higher relation between those objects. So the beauty of this whole categorical thing is that if you have an anyon model, in order for you to study symmetry, just to talk about group is not good enough. And to capture something much more interesting in physics, like a symmetry fractalization effect, it's better to promote this to a categorical group. Actually, it's more than a categorical group, it's a categorical two group. So that means a two group and a categorical put into a three group. So this is really a three group. And what is the group you are thinking? That's a categorical zero group. So that's make it a one group. So that means this categorical two group is a three group. So that means it has objects, morphism, one morphism, two morphism, three morphism. And a categorical group just means all those morphisms are invertible. And the standard group is a categorical zero group. It's a one group is you have a single object, and then all the morphisms are the group elements, which are invertible. So that's the categorical number. And then there's a generalization, which all the way go back to Quaylen and Grothendieck, which give you any kind of category. You can also define a classifying space. And I claim this categorical group, which is a three group, has a classifying space. We have a non-zero pi 1, pi 2, and pi 3, and all the pi 4 and above are 0. So that's this. I use the boldface to indicate this is a categorical group. Then I claim the space of Hamiltonians realize a topological order modulo the invertible ones. It's homotopy equivalent, means it's just a model of the classifying space. So that's the claim I'm making. And I don't have anything for you to show you that I can prove, but I will give you lots of evidence. As I said, I couldn't define the space of Hamiltonian. And this is a mathematical object. But I will show you evidence why I believe it's true. And actually, I will show you there's well-defined map going back and forth between the homotopy groups. And for those who have never seen classified space, let me convince you why this is possible. So let's forget about categorical group. Let's go back to the we all standard group. So what's the classifying space of a group? So the example if you keep in mind is take the integers. And then the classifying space of the integers is the circle. And the circle is described as the quotient of the real line modulo the z action. So what it means is that in order for you to get a classifying space, all you need is a carving space, which is contractible, and then your group acting on freely. Yeah, so that's what you need in order to get a classifying space. And now I want to say, obviously, the categorical symmetry group acting on the space of Hamiltonian. And that's almost by definition. What's the symmetry of a theory? The symmetry of a theory, normally you say, oh, it's preserved the Hamiltonian. But we are in a better situation. We're in a phase. I don't need to fix the Hamiltonian. I just need to move to a Hamiltonian which realize the same phase. So therefore, that's not surprising the symmetry of a topological order acting on the space of Hamiltonian. And it's just more subtle than that. What it means is that you need to take the symmetry of the topological order, and then you take the space of Hamiltonian, you put them together, and then twist them to get into a contractible space and the group action freely. And that will give you what this conjecture is about. It's the same thing if you think about how do you go from R, Z, and the circle. You take the circle, you cross Z, and now you have infinite many circles, and then you open a circle, twist it, that's give you the real line. And that's the same story here. So that's basically what I want to talk about today is this conjecture. And I don't even have a definition, but I will give you evidence why I believe it. So leave a lot of time. So okay, so now we'll first now have the yin and O. So I already mentioned. So if you take an anyon model and the yin and O calculate the homotopy group. So the fundamental group is the Picard group, or the tensor autoequivalence. And the second homotopy group are all the abelian anyons in your model. And the third homotopy group is very boring. It's always the non-zero complex numbers. And they're all higher than 1. If you take the toric code, pi 1 is Z2, and that's the famous anyonic analog of EM duality. And pi 2 is all the anyons, Z2 cross Z2. So now you can see the classified space have lots of topology. And now I want to give evidence why I believe the space of Hamiltonian behave like the classified space. So I will give you a map from the fundamental group of this space of Hamiltonians to invertible domain walls and back and forth. And I will just give you cartoon pictures. So the first direction is I want to go from domain walls to a parameter family of Hamiltonian closed path. And this is very topological. I will do so-called Morse move. So what you do is you take your topological order. And then once you have an invertible domain wall, you can write down Hamiltonian or a neighborhood of the vertex so that the Hamiltonian give you this domain wall. This is the same topological order, but now you have a gap boundary. And then you continue on to one skeleton, two skeleton, and eventually you extended everything. So now what you have done is you have pushed the invertible domain wall through the whole topological phase of matter. And the beginning and the end have be the same topological order, so you get a loop. So that's how you push the domain wall into a path of Hamiltonians. And the other way, go from a path of Hamiltonian to domain walls, that's just completely analogous to Kitaev did for the invertible case. You unroll this family of Hamiltonian onto the last factor of your space, and then you can argue physically there would be a domain wall between this thing. So that's basically his idea of unrolling. So that's from pi 1 to domain walls. And now I want to do pi 2 to abelian anyons. And there's a similar story about unrolling. If you have a 2-parameter family of Hamiltonians using Kitaev idea, you can unroll it. And I claim that's to be indicated as a abelian anyon. And I want to go the other direction, which is how do you realize, suppose you give me a abelian anyon, how do you realize it's by a 2-parameter family of Hamiltonians? And I will do the toric code. And in general, we have an argument for any quantum double, which means they are realized by the level 1 model. So if you want to realize the fermion in the toric code, that's actually relatively easy. You just take Kitaev, Majorana Hamiltonian, realize the trivial order, but now in the odd fermion parity. And that will have actual, basically, abelian anyon sum. And the difficulty to realize E and M. And I really won't give you the detail, but I just quickly tell you how we do it. And what we want to do is we want to define a Hamiltonian on the plane, which is spatial dependent. And we want the anyon to be sitting at the vertex, at the origin, and then sufficient large radius outside. It's just a toric code. And the way we do it is basically to first working on the x-axis, the y-axis, try to conjugate the Hamiltonian using polys, and then do a neighborhood of the x-axis and y-axis, and eventually extend to the quadrant. And into the quadrant, we need some topology. We need to calculate some. We need to claim certain space of Hamiltonian is simply connected. And again, it's described in the paper. It's nothing rigorous. So that's how we go from pi2 to a billion anyons. And I have no idea how to do pi3. So the young people here might as well think about how do I do 3-parameter Hamiltonian to a invertible complex number. And for those who really want to try, pi3 has a name in categorical theory. That's called modification of natural transformation. So that's actually is the modification of the identity of natural transformation. So that's actually what I want to tell you, basically a conjecture that the space of Hamiltonian is behave as a classified space of symmetries. And I want to tell you, how do we think about this? So we actually thought about something completely different from here. So what happened at Microsoft is that Matt Hastings and Zhenghan Wang invented some new kind of a quantum error correcting code. So if you think about the history, I think Peter's here. So he invented, I think we call subspace code, which is error correcting code, which is a subspace. And then later on, he found that it's better, the subspace has a tensor product structure, and then this will tolerate more better, and that's called subsystem code. And what Zhenghan Wang, actually, so Matt Hastings and Zhenghan Wang discovered is that for our particular hardware, the Majorana quantum computer, there's something better, which is called Floquet code, and which is trivial as those two kind of code, and it's dynamic. So the example they did is called Honeycomb code, which is the best code for Microsoft hardware. And it has only 2-qubit measurement, poly measurement, has a very high accuracy threshold. The design layout is much simpler than surface code. So that's where we started. I will tell you what it is. And then we try to understand as a mathematician, once you have a single interesting example, I want to know all of them. So that's how we came out with this Hamiltonian explanation, what this code is. And so let me tell you the Honeycomb code, which is incredible. It's really a game changer for Microsoft Majorana. So this is the following. You take the Honeycomb code, or take the Honeycomb lattice. You put a qubit on each vertex. And then you color all the plaquette with a 0, 1, 2 in this particular pattern you can easily see. You color all faces with a 0, 1, 2. And then I claim each edge now have 9 different labels. One is if you extend the edge, we'll hit either, hit a 2 plaquette, they're always the same. So we'll get a 0, 1, 2. And also each edge have a direction. X direction, I don't know, Y direction, and then Z direction. So each edge get 9 labels, 0, 1, 2, or X, Y, Z. And then what you do is you take the qubits on the vertices, and then you measure in 3 rounds. So for all the edges with 0 label, at the 0 round, you measure the 2 qubit at the end, and then the poly, which given by identification is a poly X, poly Y, or poly Z. So if you do this one, you measure the 2 poly Z on its 2 qubit at the end. And you can show this is a trivial subsystem code. But dynamically, this has a toric code ground state. And the toric code is not in this particular way. It's on some kind of cross-graining lattice. It's on this bigger Honeycomb lattice. And there's a standard toric code there. So every time you measure, you change the toric code subspace within this bigger Hilbert space. So there's a dynamic toric code inside this bigger Hilbert space. And it has a much higher accuracy threshold, only 2 qubit measurement, and very easy laid out for Majorana qubits. Perfectly for us. It just beat surface code for us completely. So that's what they invented for our purpose. And then my question is, what this is. And I still don't know, but the explanation is this can be generalized to something called automorphism code, which is basically the following, which I want to claim, but I don't have a construction. Give me any anyon model. give me any symmetry. I believe you can make a new code called Floquet. For those who don't know Floquet just means time periodic. So what it means is that you can realize the symmetry in sequentially in a loop. And I claim you realize in the right way, you will get a new error correcting code, and normally with much better property. And the one we did for toric code, we want to try our new idea to get a new code, and we did. And it turns out it's not quite the Hastings hard code, but it's very close. And the key construction is the famous Kremers-Wangen duality. And we call this the Kremers-Wangen circuit. So in this context, just that you pick a sigma loop in a Floquet and then fuse into the boundary qubit. And again, it's described in the paper. And I think I will go to my slide and then take questions. So I think I don't give you any details, but I give you the idea what we are interested in. So basically, what I'm interested in is give me a topological order, and I'm interested in the moduli space of Hamiltonians, which realize this topological order. And this tautology, this is an invariant of the topological order. It's just something attached to it, just like I'm an invariant myself. And then any invariant you derive from this space are also invariant of this topological order. And now you can ask the question, can you get better invariant of topological order? And why this question? I can give you specifically what I'm thinking. So let's consider anyon model, which I know very well. So the anyon model have very good invariant, which is the modular data, modular ST matrix. But they are not complete. They cannot distinguish the anyon model. So what you really want is easy invariant, but complete. And those are normally tension. If you want complete, normally extremely hard to calculate. And you want to good, normally pretty floppy. So the right balance is extremely hard to get. So my question now is, suppose I give you a topological order and I give you the space of Hamiltonian. Can you derive first the modular ST matrix? And if you can you go a little bit further to get something like what I would call a good complete invariant of the topological order? And I have no idea, but I think it's something possible. I think I'll stop here. Thanks for listening.
Zhenghan?
Thank you very much for exciting talk and staying on time very much. So we have plenty of time for questions.
Yeah, I wonder from this model data, can you compute this invertible domain like compute the pi 1?
I don't know how to get that actually. I think you might need a little bit simple. I think you can get, some I think called modular invariants, but I don't think that's enough for you to determine what it is. I think there's, Victor might, I think there's something of very subtle. Well, I think there's another context example to model data determine anyon model, which is some paper in Davidoff, something called Vogel multiplier. I think there says, there's something very subtle. I don't know.
So this is very beautiful work of cataloging various types of invariants of the topological order. I just make sure do I understand correctly? Are you, when you say here, when you say good complete invariants of topological order, are you conjecturing that this particular form of invariance, that is the space of Hamiltonians, gives you all the invariants of the topological order?
That's what it's all inside words. So when I say the Hamiltonian realize the topological order, so that means everything of the topological order should be able to derive from the Hamiltonian. So therefore, I consider this is a complete invariant.
Oh, I see
So
you're defining a topological order.
defining,
Right.
yeah, since it's a tautology.
Okay, well, then I agree with you.
Yeah, well,
Otherwise, I was going to disagree.
but I think that we're subtle things. That's why, what I said about, the classifying space, there's something, for example, the categorical symmetry extremely hard to catch in reality, like Misha want to do in the lab. But other hand, symmetry fractalization is a real physical phenomenon. And that need, the categorical part. You just cannot think about, what do we think as a group, premier things, classical we can see. There's something a little bit more. I think this is in that direction.
Thank you for the clarification.
Zhenghan? In the special case that the topological order is a Greenfield center or a double.
Yeah.
What would be the role of the space of commuting projector Hamiltonians?
So, we all show got here. We all know how famous, level 1 model is. But let me say something bad about the model. So, I think this is about the control. Yeah, this should be working. So, when we try to realize the, toric code or Floquet code generalization, and we realize the level 1 model has a defect, and we have to try to fix it. We don't have a good fix. So we all know Kitaev wrote down not toric code, but any finite group, the double he write down Hamiltonian. And it's just not general to realize all the double. But in retrospect, Kitaev Hamiltonian has something better than the level 1 model, which is the vertex code, the vertex term and the Floquet term are defined independently. You don't need to sequentially first take the vertex term, then implement the Floquet. And that's actually cause a problem when we want to do the code, which is we don't know how to implement a loop onto the Floquet when the vertex violate the solution. So that's actually we have a problem. So we have to use somebody else, which is the so-called entangling debrief. There's something very, I shouldn't say bad, but it's not very natural extension to do that. Back to your question. So the Floquet term basically implement, it's part of this circuit which I draw, which is this so-called perennial one duality circuit, which is for you to do the time step. The circuit, basically the way we construct a loop is we construct a discrete number of points and then try to interpret those things. And those Floquet terms basically used for you to interpret this thing. And we use the topology, very easy lemma, which is you fix the Hilbert space. If you consider all the Hamiltonian, which permission matrix, which is isospectral with the same multiplicity of eigenvalue. I hope I did the topology correctly. The fundamental group is trivial. And we use that to interpret between edges.
So that kind of leads into my question, but more from the earlier part on your Homotopy Conjecture. So I know like when you're talking about these like pi 1 and pi 2 gave like sort of examples with the toric code on like sort of these tricks that you can do to get the intuition. You mentioned that it works for quantum double, but like I wasn't sure exactly like what happens when you introduce the non-abelian anyons and like how it.
That's what I answered my question. So in the paper, we have a outline how to do it because of this defect of the level 1 model.
Yeah.
I think I'm pretty sure it's worked out hard enough, but that's not my preferred way to do it. My preferred way to do it is to generalize K-type of model using Wyckoff algebra. And then that will solve this problem of sequentially do the Floquet term. And I think toric construction should be relatively easy to generalize. But I have no idea how to do it yet.
So since you're allowing non-commuting terms in the Hamiltonian, it seems that you can, you're classifying sort of static Hamiltonians with topological order, and you allow for non-commuting terms. And non-commuting terms are natural in the context of the time dynamics of the Floquet codes that you consider. So do you expect a complete topological classification also of the Floquet codes? Like, I guess what I'm asking is what makes time special in the context of Floquet codes and different from space, given that you're allowing non-commutivity?
I think they are a little bit special, but on the other hand, they are really part of well, first, let me make a comment about I don't believe non-commuting is important. I believe that the homotopy of the whole space, including the non-commuting one to the commuting one. But then for the time, it turns out what the actually first time when Matt Hastings started the part thinking about this, we don't believe this is a code. And the reason is there are certain errors on the plaquette in space you cannot deal with. Later on, I realized in order for you to encode certain property, you have to go to time direction. So I think in this particular situation, the time direction basically is the dynamic which realized the invertible, which is part of the symmetry. So I think it's just the way all topological order is that. I think that direction is still special because of this continuity. I don't know if I answered your question well, but I think it's fair.
Maybe we can talk more later. I guess I'm imagining that if you have non-commuting terms in your Hamiltonian, you should be able to simulate time dynamics with you have 2+1 dimensions in this Floquet code. Why not consider it as 3 spatial dimensions and simulate the time dimension with space?
Mm-hmm.
And do you just get the same classification completely with static Hamiltonians?
Oh, okay.
That's, I guess, my question.
Okay, maybe we are thinking. I don't think about not commuting at all because I think a homotopy to commuting.
Yeah, so I have a question too. So I know you said that for pi3 you don't know how to construct the 3-dimensional family, but one property of this family that has to hold is that it should be totally discontinuous with respect to this complex number, because every complex number should represent its own homotopy class.
Well, I think you said a discrete topology, but it's
yeah. So do you expect that this, of course, this cannot happen with finitely many states, but do you expect that this is going to happen when the number of states goes to infinity? So somehow all complex numbers will decouple from each other topologically.
I will encourage the young people to think about pi3 because I actually think it's a very important number. So I think it has to do with some kind of some other kind of anomaly. I'm using a word I don't understand what I'm talking about. I think it has to do. So I should say, how people think about these 3 fundamental groups. So what it is it's basically the high dimensional morphism. So what is the non-zero complex number represent? It represents all the possible morphisms from the ground state to the ground state. So that's it. So it's some kind of anomaly for pi3. And pi2 is a billion anyon. That's actually all the natural transformation into the identity function. So I think there's some really physical meaning there. But I think pi2 already exhausted us, so I don't know how to do pi2, but I think it's important to do with some kind of anomaly of the ground state.
So you gave some physical interpretation for the homotopy groups. Is there a physical interpretation for like the Postnikov class also? Like the H3 and the 2 groups, say.
I didn't quite.
Is there a physical interpretation for like the Postnikov class?
If I got it correct, there is a physical interpretation of the classified space.
Right. Of like in the 2 group, you have an H3 extension. You have it like the extension of pi1 by pi2. Is there a physical?
I really actually, the only physical thing I can say is like, you pump the mean water, but I don't think it's a real good. I did ask Alexa this question many years ago. I don't think there's a good answer about it. He definitely believes there are physical interpretation of all the homotopy groups, but I don't think there's a good answer.